Hi, and thank you for taking time out of your busy day today to join us here at our virtual Heron Innovators booth. This virtual booth is brand new to us, and I'm sure it is to all of you watching today. But again, we just want to make sure that you guys are having an enjoyable time here, and hopefully we are very informational. With that said, I'm going to introduce everybody. I'm Curtis Ralph. I work here at Heron Innovators, and we are the home of the suspended air flotation. Before I go any further, if you guys could just leave a little note in the chat and let us know that you can hear us and see us. Maybe you don't really want to see us that much, but at least hear us. Looks like we're up and running. So. Let me introduce John Barsotti here. He is the president and innovator of Heron Innovators. I would go on and on and on because he does sign my paycheck, but we don't want to listen to that all day. Also is our vice president of sales, Jeff Knolenberg. Jeff is unfortunately unable to be with us here today, but he is quarantined back in Kentucky. And to be honest with you, most of us here are a little bit happy about that. Other than that, Jeff's a good guy. So if you have any questions during our presentation, please write them in the chat box, and at the end of the presentation, we will get to that. So without further ado, today we're going to talk about why our SAF results are probably pretty new to most of you in the wastewater industry. Much better results than what you're probably used to. So you go ahead and get started. John, go ahead and take over.
Thanks, Curtis. Yeah, my name is John Barsotti. I'm the founder and president of Heron Innovators. I've been doing this for 20 years. The company started in a backyard in 1997. So we have a unique process, and we hope to share some information about that with you. I want to thank you all for joining us today. I know with this COVID virus that's kind of affected all our lives, it's not the easiest thing to do these kind of events. We would much prefer to be face-to-face with you down in New Orleans. So, or Chicago, I'm not even sure where it was going to be this year. It got canceled so long ago. Anyway, we hope to take a little bit of time today, go over some of the amazing results and how robust our process is, and some of the cost benefits of operating our systems. Jeff Knolenberg is Vice President of Sales. I'm going to have him introduce himself here in a minute, and he'll begin the presentation, and then we'll have a question and answer session later. Again, we're not real used to this, right? We're much more comfortable on a face-to-face environment, so we are going to miss things. So please use the chat function to submit your questions. We will answer them as best we can here, and if we can't answer the question here, we will follow up with you afterwards. All right, Jeff, you're on.
That's done. Thank you, Curtis. So I'm going to switch to some slides. Let me know when you can see these. Is that up on your screen?
Looks good to me.
Okay. All right. Thank you. So I first became acquainted with Heron Innovators maybe 5-6 years ago, walking a trade show. I came from the centrifuge world and actually worked for a company at the time that built they integrated centrifuge systems. So we built skids, and I was focusing at the time mostly on spinning DAF solids with centrifuges to break emulsions. And I think it was a show in Atlanta where I ran across a guy that in the conversation he mentioned this SAF technology to me, which I had never heard of, but he said, you need to check it out. It's a great technology. And so I called up John, and we started talking, and I started telling a few of my clients about it. And I guess a number of years later, I ended up going to work for Heron Innovators because it is a great technology. And in fact, it had much more benefits, or many more benefits, than what I was looking for. I was looking how to break emulsions with the centrifuge, and I had heard you could get by with less polymer with SAF. I'm thinking polymer creates an emulsion. I'm trying to break that emulsion. Less might help. And in fact, you can get by with less, and it does help. But there's so many other benefits to SAF. And the title of our talk this morning is actually SAF achieves results you've learned not to expect. Flotation without dissolved air. So we're going to start by going through a jar test right now. So this, again, was a couple years before I went to work for Heron, and I took this video with my phone. That's actually John standing in the background, and this is a tube coming from a lab unit. This fluid in this jar came out of a wet well that we had grabbed that had gone septic. It had sat for several days. The pump was down. This stunk. This was very odorous material, and I don't know if it's coming through on your screens, but there is a pin flock. We put in just a little bit of coagulant, a little bit of polymer. There's a pin flock there. And what we're going to do is inject this charged microbubble froth. And I think what you'll see is those particles are actually getting bigger as the air attaches to them. And you see we get a very high capture rate, a very fast rise rate, and a very robust float. And I had the environmental manager of this company standing next to me, and he let out a wow, that's really something. So he and I went around and looked at 3 different installations, one in Missouri, one in Kansas, and the third one was in California, where SAF was installed in all 3, but on that California, that was actually on anaerobic biosolids. And it was amazing results as well. And in fact, that was presented at WEFTEC a couple of years ago, that particular installation. So let's start off with, we made or what we said was flotation without dissolved air. So let's talk about how we do that. Get to the next slide. So let's talk about what traditional flotation is that uses dissolved air. And at first glance, SAF looks very similar to DAF, or dissolved air flotation, but when you really dig into the mechanics of how this works, it's a very different technology. So a DAF, what you've got is your influent coming into a flotation cell. And then there's usually some kind of recirculation going on where you're grabbing the underflow off the bottom of that cell where the water is theoretically cleaner. You've got a recirc pump pushing against back pressure. You inject in compressed air. Under pressure, air dissolves in water up to a saturation point. What that saturation point is based on the physics of the process, temperature, pressure, how dirty the water is, but you're going to hit a saturation point. And then when that when that water and air re-enters this flotation cell, now you're at a lower pressure. All you've got is the head pressure of the vessel. So little bitty soda pop bubbles are going to come out of solution to float those solids that we flocculated with chemistry upstream, float those to the surface, and there's usually some kind of rake skimmer here where we're going to skim those off and dispose of them. So that's basic DAF. And that technology's been around for 100 years. It's what we think of as a conventional or traditional flotation. There are permutations of this design where you've got cavitating pumps and sparging in air, but we're going to do something a lot different. There's going to be no dissolved air involved at all. So instead, we've got a froth generator. And this is just a little skid. The physical footprint's about 4x4, 4x6 in size. And what we're going to do is create a charged microbubble froth and inject that into the stream right here and stir that charged microbubble froth in. And I'm going to ask John to describe that froth and those bubbles, because you might think that, well, in fact, let me explain. There's 40% air in this froth. Here you've got somewhere around 2 to 4% air with a DAF, based on what the saturation point is. We're not dissolving air. We're creating this froth with the surfactant, injecting it in, which is 40% air. So we've got a lot more air, but you might think, well, can't you just inject more air? And there are technologies out on the market that do that. They just sparge more air in. But these bubbles are much different. And then they're going to be stirred into the process with something that looks like this. So the influence coming in here, froth's injected here, and they're going to be stirred in very gently to get a good air to particle reaction. And then it enters the flotation cell. So John, I started to say earlier, how are these bubbles different than what you might see with this technology?
Thanks, Jeff. So, I like to say that we're not bound by the physics of what it takes to saturate air and water. It's because we are actually making a soap bubble. What we learned how to do is create a population of bubbles that are 7 to 25 microns in diameter. They're actually double walled. They're in the literature they're called an afron. We do, like as Jeff said, in our whitewater, we're not restricted by those physics, and so we're not looking at 2-3%. We're looking at 40% or higher even air in what we call our whitewater. It's nothing like a DAF whitewater, of course. Those bubbles have a surfactant sheath on them, and they have a charge on them. They're anionic, cationic, depending on the surfactant you use. And we, because of the bubble size, we get a really good attraction to the particles electrostatically. But the big thing is that we have a surface tension advantage to a DAF bubble, and that surface tension advantage overcomes the surface tension of the particle, and so we get a lot more air on those particles. Between the size and the charge and the air, we have about 1,000 times the affinity for a particle that a DAF bubble does, and we actually participate a bit in coagulation lightly. But that does translate to some significant chemical savings. The other thing that is kind of noteworthy is the amount of research, because our whitewater is 40% air, so we're moving around, even not taking into account the lower air to solids ratio we need, as our air doesn't coalesce very quickly. We're cycling around something greater than 120. Or less than 1/20th the white water that a DAF would cycle. We're not really recycling. We use so little water that we end up, almost all our clients use fresh water. So right now I think I'm going to pass this back to Jeff, and we'll be back with a little bit more on that later.
Yeah, thanks, John. So let's talk about those benefits that this whole process, doing it this way instead. In fact, I want to mention that a lot of our work is in converting existing dissolved air flotation systems over to suspended air flotation. And that's generally how we start working with clients, is that they've got a system that either isn't performing well, they don't have the throughput capacity, in fact, they may have had the throughput capacity at some point in time when this was originally installed, but things have changed in the plant. So their DAF may not be working as well, or maybe they're experiencing high costs. So that is a lot of times why we get into clients where we convert DAFs over to SAF and just create all kinds of benefits. So let's talk about those benefits. And then we'll be going through a couple case studies of where that's actually been done, where we've converted DAF to SAF. So in fact, I forgot I have these pictures. John, if you want to talk about these just a little bit. So we've had diagrams, so now we've got actual pictures of what this equipment looks like. So, John, go ahead, explain this.
Yeah, thanks, Jeff. So up in the upper left corner there is an actual flock mixer on our model CF1000 float cell. And that you can see the motor and the gearbox is driving a paddle mixer that's attached to a VFD, so that we can control the mix energy going into the unit. You might ask why we need that, and in the DAF world, where you need volume to get enough air. You're moving around 15, 20, 30% of the water, depending on the waste stream. That's going to mix we're normally looking at I call it a recycle stream or a whitewater stream. That's something around 1% of the flow. I need to mix that quickly without disrupting the flock, so that we kind of evenly react the flock aid with all the incoming water. We see really good advantages of using that, and we've got it on all our installations, including the conversions now. To the right of that is an SAF generator. That's our secret sauce. That is what makes the foam, what we might call whitewater, and that gets delivered to the process. Any pressure we see in that canister is just basically to create agitation and deliver to the process, as we build no pressure outside of that. And then the screen on the bottom is a serpentine. Traditionally, you see that in a lot of DAFs today. We normally don't use that if you're just using a polymer or no polymer, or even with the polymer, almost every one of our installations, polymer's fed near the very end of that, maybe in 1 or 2 places. Otherwise, that's just residence time for pH control and coagulation. On the right is the what we call our clear floater, and that one there is a CF 1000. It's spec for 2,800 gallons a minute. I know in a recent installation, Jeff will talk about in a little bit, we've run that as high as 36 pounds per hour per square foot on waste activated sludge and primary solids. So that's, if it's not lost on you, that's 140 square foot float area. It's 20 gallons per minute per square foot, nearly. All right, Jeff,
Yeah,
back
so
to
the
you. Yeah.
footprint of this, if this were a traditional flotation, conventional style of dissolved air, this would be much bigger, right, John?
Oh yeah. 140 square foot couldn't do 2,800 gallons a minute.
Right.
In something
So-
that's got, where we're feeding in several thousand parts per million solids.
So let's talk about what we see here as far as horsepower difference, starting off with just comparing the two technologies. And John, feel free to jump in anytime, but obviously with dissolved air flotation, you've got that recirc pump that has to push against pressure and recirc enough water to get the air into the flotation cell to lift those solids. In fact, that air is lifting the solids from underneath. There's no physical attraction. In fact, that air wants to repel from the solids because of surface tension. And that's a huge difference between DAF and SAF or any other technology where you're sparging in air. So the fact that we're not feeding any air into the flotation cell at all, we're attaching all that air, those air bubbles, to the particles ahead of the flotation cell. That shows how the technology works. There's no more air injected into the flotation cell to keep that solids blanket suspended. So all that takes a lot less horsepower. And John, you got any other comments on that?
Well, yeah. So I think all of us are trying to encapsulate air in a developing particle, and but because of our surface tension advantages, our particle is far more easily enveloped into a developing particle, and that's why we get so much air, and that's why we get such fast rise rates, and that's why our footprint's so small. The DAF bubble has a surface tension disadvantage. It's very hard to encapsulate with any degree of efficiency an air bubble in a developing particle in the DAF world, and that's one of our large advantages. The other thing too I wanted to point out twice is to say that you see a difference in horsepower on that slide. We're at about 10% that of DAF. Again, our horsepower is not about, a DAF's horsepower is in moving a certain volume of water under pressure to saturate it with air. We don't need to do that. All we need to do is create a controlled agitation environment, which we do in our SAF generator, and then the ability to deliver that stream to the process. So it is, even though we say ours is 30 PSI, we're oftentimes around 10 PSI given some compromised situations. And again, the pressure is not that important to us. Therefore, the horsepower savings are real. Jeff?
Yeah, and of course another contributor to horsepower with traditional flotation is an air compressor. We don't have an air compressor because
Exactly, right.
we're making this bubble at atmospheric pressure. We're actually drawing that air into what we call the can on the froth generator and making that bubble at atmospheric pressure. So, and another thing that occurs to me to mention is that we talked about traditional flotation and hitting a saturation point. So the warmer that stream gets, the lower that saturation point is going to be. In other words, the less air you can get into that water. So SAF really does not have the same constraints at all on warmer streams. And in a lot of industrial applications, we come in, we're running, in fact, I had one come up just the other day that was 170 degrees F. And they were wanting to, or they actually were running a DAF and seeing it actually not really accomplishing much. So we don't have that constraint, right, John?
That's right. You know, so if you think about the physics or the solubility of air and water, it's based in part on temperature. So the colder the water, the more air you can a higher amount of air you can put, you can dissolve in the water to reach saturation. The warmer, the less. And we're not trying to dissolve anything in water, so it's largely unaffected. I mean, 170, 180 degrees starts getting to be so hot that it breaks the bubbles. But I know we have one installation that runs at 190 degrees. I would suggest that as we approach 200 or hotter, we would have our own trouble. But at that point, you know, the vapor pressure of water is almost out of air, and you're not getting any air in the water on DAF at all. So, Jeff?
So let's talk a little bit about the amount of surface area that's needed. John, you mentioned a very fast rise rate. You know, I guess that speaks for itself. Anything else you want to say about that?
Well, the surface area affects two loading parameters. One is the hydraulic and one's the solids flux loading parameter. So in the hydraulic loading parameter, we have data that shows we can go to 20 gallons a minute per square foot. Unfortunately, we don't reach that pinnacle that often, so I can't tell you that we can do 25 or 30, though it appears we can go above 20 gallons a minute per square foot. Up to about, I think we've seen as high as 45 pounds per hour per square foot solids flux loading. So when the hydraulics of the process brings in enough solids where now you're dealing with a solids flux limit, that's another huge advantage we have. Because the solid is so robust and the process is so robust and the solids their buoyancy is so high that the solids actually sit in a clear line above the water. There's no rag layer, there's none of that, right? And when the skimmer comes on, we're actually trying to remove the entire bed of solids with the skimmer instead of trying to cut a little bit away to get it drier, as you'll see in a DAF. And so that contributes to these solids flux rates, which is another big loading parameter advantage we have. DAFs, when you start talking things like waste activated sludge or biosolids, of any kind, you're starting to talk kind of loading limits of 7 pounds per hour per square foot. Most engineers spec it at 2 gallons a minute per square foot. Even primary solids with a lot of fat, it's really hard to get around 10. We're easily in those things above 20 pounds per hour per square foot. A little bit of fat. Well, actually, we just did a few trials now on anaerobic solids, and we're in the mid. We don't sell equipment or specify the catalog item at 45 pounds per hour per square foot. But we have data where we've exceeded 45 pounds per hour per square foot with no apparent change in water and the water quality. Jeff?
Yeah, and so which brings us to our next subject as far as what the percent solids are coming off the system. And I think, of course, it's becoming more and more of an issue, especially in industrial plants where they've got solids to dispose of. And of course, the more water that's in those solids, the more you've got to pay for trucking and just the expense of getting rid of those solids. So the difference between 3% and 6% solids is not 3%. The difference is twice.
100%.
We've got half as much water. between 3% and 6%. So, and of course, those numbers, that's referring more to what you would see in an application where we're dealing with biosolids. But in primary solids, we can easily see those numbers. I know that in some industrial applications, what we're seeing those numbers in the 20 percentile range on percent solids coming off the DAF. Or SAF, I'm sorry, SAF. And we're going to talk about that a little bit more when we get into our case studies. But why, John, do you think that we see such a higher percent solids coming off SAF compared to DAF?
It has to do with how well the air bubble engages the particle and how light the particle is in solution and how robust a solid it makes. I think it has a little bit to do with that coagulation property I talked about earlier. But it sits very high in the water. It dewaters very well, right? It's not sitting in the water. I don't have to get my rake on my skimmer to cut half the solid blanks off so that I can catch, the top half of the solids blanket so it's drier. This stuff, except for the layer that's directly in contact with the water, has been draining the whole time it's been sitting on top of the float cell.
Yeah, and often we see other dewatering or even drying equipment downstream of our equipment. So obviously, if we can get the solids drier and prove that, when the original equipment's put in, we can actually get by with smaller equipment, smaller capital costs on that dewatering equipment downstream. And we've got a number of case studies where we've shown we've been able to cut the centrifuges that were used in one application in half, just because the solids were that much thicker. So, John, I think you hit on talking about our whitewater. Our version of whitewater is actually our froth compared to a DAF, which has a recirculation stream. And of course, we're not recirculating any water. We're not pulling any water off the underflow of that flotation cell. And there's some benefits to that as well when it comes to starting a system up. In fact, John, you and I have talked about this just recently about trying to start up some problems that we've seen with conventional flotation. What happens when you're running those flock solids back through a pump? You want to comment on that, son?
Yeah, in a real world where you don't have perfect water, in a DAF environment, you're taking, a lot of DAFs are hitting around 70 to 80% removal efficiency in waters where we're doing like 95 plus. Well, there's solids left in that water, right? It's 30% of what came in. Those solids might be in some stage of polymerization or flocculation, and they're going to end up going through a recirculation pump and getting macerated again. Well, those become very difficult solids to treat. And so a lot of the manufacturers, depending on the water, will use some sort of freshwater source to start up the unit. And then if the water ever clears up, they switch over. And what happens, they end up saying, the flows are huge, so they switch over. And that can impact long-term treatability of the water. We don't have that problem because most of our clients, because what we would call our recycle stream is such a low flow, they just elect to bring in some sort of fresh water. We have some installations where we have recycled water, where we actually pull it out of the bottom of the tank, similar to a DAF. But even at that, we're looking at usually about 1% of the flow, 0.5% of the flow. It just doesn't have the impact, even given that we might experience the same problem. It just doesn't have the impact that you see when a DAF's recycling 10, 30, 50, 100% of the flow.
Yeah, in fact, you had mentioned earlier that our water that we're injecting in as part of that froth is, I think you said 1/120th of the actual flow. So I think, and in fact, I did just run through that math yesterday, and I would concur that's the number. In this particular example that we've got up, I think the incoming was 1,000 GPM. I'd have to work to see if that fraction still works out, but should point out that the 6 GPM that we've got shown there, that's 6 GPM of froth. So 40% of that's air.
All right, so
And
so
percent is water. So that's really only 3.6 GPM of water.
yeah, so I mean, in a lot of our applications, we'll be running 100 gallons a minute of water, You know, in most food processing plants, you'll see 100 gallons a minute of water will be running maybe 1.5 gallons a minute of froth. You'll be looking at a water commitment to that of something less than a gallon per minute. Is less than 1% if you were to call it recycle, it'd be less than 1% recycle. So with those small numbers, you have two advantages. One is you just don't impact the hydraulic capacity of the float cell very much, you know, and if there's something wrong with the water, it doesn't play in a big way with your results.
Yeah, so one other thing I want to hit on while we're on this subject that we've touched on just a bit is that startup. So since we're not recirculating water, we're not macerating those flock solids with the recirc pump, our startup is less than 15 seconds, would you say, John?
Easily, yeah. And I think we do a robust 15 seconds. You can start up almost immediately, actually. We
We get a
Jeff,
number of
let me add this.
installations. Go ahead, John.
Yeah, let me tell you why we do that. We just do that in an abundance of caution to cycle the generator up so froth is ready for the process. But that froth is developed almost instantaneously. So, but 15 seconds seems to be pretty easy to do, and so we just do it on our installations.
Yeah, so one of the first I mentioned, I visited some installations. One of those was in Missouri at a truck wash. And that was set up with the water came out of tanker trucks, that it was vegetable oil that was being washed out. It drained into a pit, and I believe there was like an ultrasonic or radar gauge that was measuring the level in the pit. And it would start this system up automatically when the pit hit a certain level, and then shut down automatically. And the operators paid no attention. There were no operators. They basically ignored the system. It just kicked on and off. I don't think you can do that with a system that takes a half hour to start up.
Yeah, I mean, our unit in that application. I'm sorry, Jeff. I didn't mean to talk over you. In that application, the unit comes on every 10, 20 minutes for 10 minutes, 5 minutes, right? Pulls the tank down, starts again. It's not, you know, as an OEM, as an equipment OEM, we would prefer longer runs, but we can do this. We're not suggesting that we go design to that if we have an option. In this case, we didn't have an option, so.
Yeah, and I've had this come up a number of times in the last few months, that when you go to size EQ tanks, the way you think about equalization ahead of a system is a lot different with a SAF than what it is with conventional flotation, because we especially when we get into the smaller flow plants where maybe there's only 20, 30,000 gallons per day coming out of the plant, we could run at let's say 25, 50 GPM when the system kicks on. That EQ tank, of course, often you use jet mixers to keep them aerated, but essentially when you've got wastewater sitting in a tank, that's a fermentation vessel. And you are going to get ammonia buildup. And of course, I had one engineer mention to me, he said, you can just never have enough EQ. And I said, well, he said, I've been doing this for 40 years. And I'd say, well, if I were putting in DAS for 40 years, I would agree, because it takes a long time to start up a system. And you've got to have that buffer. But with our system, with the SAF system, you're up and running in less than 15 seconds. So you can keep that level in the EQ very low. You get less chance for ammonia buildup and other problems that can occur. Anything else to add, John?
Yeah, so there's two reasons why we get by with lower equalization. One is, not a reason, but DAFs are finicky pieces of equipment. They really respond poorly to process changes, right? So the whole idea of the EQ in a DAF is get this kind of steady, perfect water as best you can the whole day, and have it run long and hard, long and slow, so you're not turning it off and starting it up. We really don't need to live by that, right? We can start up and shut down quickly, and one of the reasons we can go to these smaller EQ tanks is we got a really high tolerance for process variations. And I think a lot of our customers will tell you, when we were using DAF, we had to worry about, every day, every hour, so we come out, see if our water had changed, if we lost the treatment. Because, man, we just start this and we sometimes don't look at, I have customers that don't look in on our unit for 3 days. They'll have an EQ tank, it'll go on and off automatically, and they won't look in the unit for 3 days, once, twice a week. I don't recommend that, but it's because just the process tolerance, it's such a robust process. I think, and then I want to comment on the ammonia issue. Yeah, these large EQ tanks tend to go anaerobic, and if you have protein in the water, it tends to break down the ammonia, which has been a problem in a lot of our packing and protein plants around the country. So we've oftentimes been able to come in and greatly impact that problem by saying, why don't you just use about a quarter of that EQ tank? Don't use that whole EQ tank, and just have us come on and off as needed. So, all right, Jeff.
In the interest of time, I'm going to jump to our case studies.
All right, okay.
And so we talked about retrofitting DAF to SAF, and it just takes it takes two components really. It's a matter of putting in our mixer, and as we showed a picture earlier. So we'll custom build this mixer. Of course, this picture was taken in the shop. So what you've got is a drive on one end that's controlled by a VFD driven motor, and then so the influence coming in here, frost injected here. We're going to stir that in very gently where we get that air to particle reaction just before it goes into the float cell. So these are custom built to fit the existing application. We're going to be talking about two specific case studies where we did retrofit DAFs and convert them to SAF for one reason or another. So, and the first is, we'll start off, that both of these are out of the same plant. We've got a primary DAF and a secondary DAF that were both converted to SAF. We're going to start off with the secondary, which was treating, these were aerobic biosolids. And again, John, if you want to jump in on any of this, feel free. But so before it was a DAF, or when it was a DAF, the flow rate was about 1,250 GPM. Our mixed liquor suspended solids level was about 1,500, and they were getting about 60 to 70% removal with that. And then, of course, after that was converted, there's times when they'll run that up as high as 3,500 gallons per minute and hit 3,500 mixed liquor suspended solids again. But running it on an average about 2,500. In fact, I'm going to jump out of this presentation because I've got a spreadsheet that actually shows the performance on this unit. So let me pull that up. Is this spreadsheet coming through?
Yes.
All right, so this is 2019, and the environmental manager at the plant was good enough to send this to me. So again, 2019, and of course this column G is the removal that we're seeing. So this is clarification of mixed liquor solids, and so we're as you can see, we're getting consistently better than 99% removal. And he told us that it was normally running about 60 to 70% removal back when it was a DAF. And in fact, I've often brought clients into this plant and showed them these systems. John, I think you have too. And one day last fall, in fact, I think it was October, it was, let me see if I can find it, October, right here, Thursday, October 10th, last fall. I had a potential new client with me. He wanted to see SAF in operation. We walked into the lab before we walked in to see the unit, and the lab manager looked up, she saw me, and she said, "Oh, I wish you would have been here this weekend. We had a little upset in our plant." And I'm thinking, oh, that's not good, especially when I've got potential new clients standing here right next to me. And she said that Lovejoy coupling on your froth generator went out, and maintenance decided not to fix it until Monday. That happened Saturday. The reason they decided not to fix it is because they still had the old dissolved air system on that particular unit that they could just switch to it. Turned our froth generator off, or it was already off because that coupling went out, but turned the dissolved air system on. That was Saturday. And so this is the best example I've got of all things remaining equal, DAF compared to SAF. This was the day that the SAF became a DAF again. So you can see the difference in removal on Saturday, Sunday, and then of course Monday, that repair. They had the Lovejoy coupling sitting on the shelf, in fact, about a 15-minute repair, and they're up and running again. John, you got anything else you want to add on that? I'll get into some actual numbers on costs on this, but anything else?
I actually think we ought to move on, Jeff. We're kind of running a little bit low on time, so.
Okay, so let me see if I can start this up again.
All right. I might mention that the site, that site now has, that company now has 9 of our units in. When they put the first one in about 3-4 years ago, I think. So they're definitely, they've told us straight up they'll never buy another DAF.
So this here's our froth generator. Here's the mixer, and again, this was custom built for the application. The next table is going to show. They actually did a presentation. This was in the poultry industry. U.S. Poultry and Egg has an environmental conference every year, or most years, and several years ago they presented this. So it shows we turned off 60 horsepower on the recirc pumps, replaced our skid had 10 horsepower, and then this shows the cost of the surfactant in this application. So we're not forgetting that, but coagulant and cationic polymer that they were using back when it was a DAF, and then after they converted it to SAF. So even with the additional flow rate, the additional loading, and of course they realized really clean water after that, so much so that they could use it as recirc water. They still experienced better, right at $250,000 a year in savings, just between chemistry and energy alone.
I believe that retrofit paid for itself in a few months, like 3 or 4 months.
So same plant upstream. This is the primary water, and in fact, there's a rendering plant and a poultry kill facility that water from both of those plants goes to the same EQ basin, which feeds this particular unit. Now, this DAF was performing well before they converted it to SAF. They were getting their TSS down around well below 100. Very good performance, but it was maxed out. They had hit their nameplate on their flow, and they knew they could not get any more flow through this system. But the plant was expanding; they were adding on, and I believe they had in their in their budget for their plant expansion, they were going to add a building and buy another DAF. So instead, they simply converted this to SAF and got an extra 700 gallons a minute flow through it, and then here's the savings that they saw. So before they had 40 horsepower connected, here 10 with SAF. Again, here's the cost of our flockade, our surfactant to create our bubbles, and then here's what we see in savings in coagulant. So, and they did cut out the anionic completely in this example, and reduce the coagulant as well as the cationic polymer. And even though we had an extra 700 gallons a minute through it, still realizing $90,000 a year in savings. And of course, most significant to them was they didn't have to build a building and buy another system. And in fact, this picture here is actually the top of that, and this shows how dry the solids can get. And a lot of times they'll rake these solids off, and they go into this secondary vessel where they'll do further dewatering. And I remember when they started this plant up, they called and were laughing, or John told me the story actually, that they were laughing. He said, well, they got those solids so dry that they wouldn't flow to the pump. So they had to back off on that a bit. So I know we're running out of time here. Curtis, I'm going to turn things over to you. Have we had any questions come in?
Yes, we have. Thanks, Jeff. We'll go ahead and get to them real quick. So on one of the slides, you had mentioned that the SAF requires very little operator attention. does that mean that SAF requires less operator attention than a typical DAF? And then a follow-up to that, if so, is that just because of the reduction in horsepower, overall equipment, and polymer needed, or what is the real reason for that?
Jeff, I'll go ahead and take that. You
Yeah.
know, the DAF is just much more mechanically intense than a SAF, and we designed the unit to have, other than the patented device, we use just straight OEM off-the-shelf materials, and they're generally considered very reliable. So we've had more than one customer say, we don't look in on the equipment every day, though I recommend you do, and that the only thing over years of operation they've done is washed it down once every 6 months or so and greased some Zert fittings. So our biggest problem, of course, would be like the metering pumps, which is kind of a typical Achilles heel of a lot of equipment that's feeding chemistry. And then like a water solenoid, and those are things well within the capability of even a light maintenance department. So we find that the startups are easy. They don't require someone's attention to start up. In fact, almost all our systems start on a switch somewhere, without an operator getting involved. So to the last person, they'll say that it'll do everything I said it'll do. This is when I was out there selling it, not Jeff. It'll do everything that I said it would do, but they would have bought it for no other reason than they just turn it on and walk away.
So basically,
Yeah,
you're
John,
saying,
I'm thinking of, I'm sorry, Curtis,
No,
if
go
I
ahead,
could just
Jeff.
add one more example to what John just said. We recently ran a pilot head-to-head with a DAF. And so we were there at the same time they were, and the operators from the plant got to run both systems. And with our system, they came in and they knew all they had to do was hit a button and the whole system was up and running within 15 seconds. Any changes they made to the system, we were trying to optimize polymer usage. And I totally kind of glossed over how much polymer we save. I guess we talked about that in the case studies a bit, but we were trying to optimize polymer usage, and they saw those results immediately after making changes. It was just such an easier system. So when it came time to make the ultimate decision, the decision was made simply on what they saw for a 20-year operational cost, which was primarily polymer cost, as well as, and of course, energy factors into that as well. And then the other decision was the operators all said, we want to run SAF. It was just so much easier to run.
I think they told the board of directors that the unit was, and I quote, I think, stupid easy to run, right? So it is easy to run. I mean, by and large, it's a matter of turning a switch. You don't have a lot. You don't have a lot of the balancing. You don't have a lot of those kinds of issues.
well, I can tell you, I like hearing that because if I ever lose my job here, stupid and easy, I think I can do. So I can be an operator at one of these places.
No.
All right, hey, we have another question. Are there any downstream issues when using this surfactant?
Yeah, so we get that question a lot. In fact, I'm going to say maybe 10%, 5-10% of our installations, people start experiencing, they will have had our unit in for a year or something, and all of a sudden, some downstream operation is seen foaming either in the water or in the solids, and never in the solids, I guess, maybe in the water, and we will turn off the SAF generator. We don't use enough to create a foam outside of the white water. So, we're usually oftentimes less than a part per million of the surfactant is active, and just never once. It's always been something else. There's a lot more surfactant, anionic surfactant, kind of naturally occurring in the background than what we have. And in fact, normally we remove, in a treatment system, we normally actually remove MBAS, which is a measure of anionic surfactant in solution. With regard to the solids, people are really concerned about things like digesters downstream or any kind of dewatering equipment, and we've never caused a problem. In fact, might be overstating it a bit, but I think we've always helped any kind of downstream condition. In the case of belt presses and screw presses, the material releases really easily. And in the case of anaerobic digesters, they've actually seen less foaming with our solids and more.
All right, we got another question in. What's the difference between the use of surfactant and surfactant injected into the recycle stream of a DAF?
So there's we're often held up to this criticism, right? Well, you can just put surfactant on the suction side of the recycle pump in a DAF. Wouldn't that be the same thing? And it's not, right? We're creating something called an Afron. That Afron's a double-celled bubble that's a particular size. We use infinitely less surfactant to create that foam than a DAF would apply, like an order of magnitude, right, or two. I think it's like 100 times less. So a lot of times, and then the even though intermittently that works in a DAF, it oftentimes is inconsistent and it's very sensitive to process changes and wear of the recycle pump. As the tolerances open up, the bubbles get really big, and it almost offers no help at all at that point on a DAF.
All right, and one more question. He said also, maybe I missed it, but why does SAF use so much less horsepower than DAF? And if you don't mind, I'm going to add on there. And also, why is it such a smaller footprint than what a DAF is?
Okay, so the horsepower again comes down to the recycle system and the smaller footprint. So let's start it. Smaller footprint requires less horsepower in the skimmer and the flock mixer, right? So the units are just smaller. But then the recycles where the big horsepower advantage is, and we don't try to dissolve air and water. So we're not moving a prescribed volume of water with the intent of saturating it with air to meet a certain air to solids ratio. We use the surfactant to create a large amount of water and air, not a couple 3%, but 40 or 50%. And that gets introduced. Our bubbles don't coalesce, so we actually have a lower air to solids ratio. So we're moving quite a bit less solution under a lot less pressure, i.e. a lot lower horsepower.
Yeah, John, I think you said a larger amount of water and air. I think you meant larger amount of air and water, right?
Air in water, correct. Yeah, sorry. Thank you.
All right, well, if John, Jeff, you guys don't have anything else to add?
So those of you that asked the question, did we answer those adequately? Let's move on. Okay.
All right, well,
I'm not
if
getting any answers, so I guess we did. So
If you guys don't have anything else to add, we will go ahead and finish up here. We will be back shortly with another video. Hopefully we've been informative today, and you, much like I, have learned something. All right, we will see you later.